I will present you the dynamic aggregation model, a form-finding tool to generate volumes with emergent topological configurations from a set of surfaces. Dynamic aggregation is based on cellular growth, a biomimetic technique based on cell reproduction to generate geometric proliferations, usually by adding new vertices to a mesh. And as we can see, cellular growth is constrained to generate surface-like results, usually expanding or contracting a mesh. Our objective is to add an aggregation component to the cellular growth approach, so a volume-like result can be generated, and to explore the generative implications of this strategy. We apply concepts of discrete aggregation, and we implement a particle spring system to approach this problem. To do so, we structure the geometry in nodes and links. These are organized in a locally oriented topology. This means that each node distinguishes between their vertical neighbors and their horizontal neighbors, together with a particle spring system, and associating each node to a particle and each link to a spring. We implement two types of resources that follow this orientation: topological resources and force resources. The main topological resource is the vertical aggregation, which allows the addition of new nodes when the distance between a node and its parent exceeds a certain threshold. Open an aggregation is made, the new node checks for new links to be created according to the parent neighbors. The second topological resource is the horizontal aggregation, an optional resource that allows lateral expansion of the geometry, which is also triggered when the distance threshold is exceeded. Same as the vertical one, after an aggregation is made, additional links are generated. Respecting force resources, the main ones are the horizontal springs and vertical springs. These attempt to maintain a desired distance between nodes to preserve stability while avoiding over-constrained displacement. It should be noted that horizontal springs are deactivated when the length exceeds a certain threshold value, allowing more freedom for emergent behavior. This picture displays the links deactivated, allowing a bifurcation to occur. Three additional forces are implemented: planar, hinge, and bifurcation force. The objective is to maintain a level of planarity on the strata and a level of continuity on the columns. Even if these objectives act in a lower level, our resources are defined from the local. The generation process starts by creating a set of nodes in the initial surface and assigning each one to a target surface. In this scenario, we start from a single surface towards 5 targets. Then, we can initialize the aggregation. The moment of bifurcation is an emergent feature, as this decision is taken by the algorithm. To visualize how the topology is kept, here is the same process with the deactivated links being shown. In addition, we can increase the horizontal threshold to change the moment of bifurcation, increasing the extension of the trunk and observing the change in real time. Furthermore, we can now increase the desired horizontal length to get wider branches. In the next scenario, we explore additional bifurcation capabilities, now starting from a spherical node composition towards 20 targets. This is the resulting generation process. Similar to the previous scenario, we now increase the horizontal threshold value to increase the attachment between the nodes. Finally, we generate different results according to architectural typologies to present potential applications. The first is the bridge typology, exploring these distinct levels of slenderness and attachment of the fibers. Then we have the tower typology, similar to the bridge, in this case in a nuclear composition with more extreme results. And finally, the chat typology, which further displays an emergent configuration as the starting result has isolated elements that are later completely merged into a single object. In summary, dynamic aggregation is based in a locally oriented topology together with a particle spring system, allowing us to design topological and force resources, which result in emergent configurations in a continuous aggregation process with real-time response. This contributes to our model in three factors: differentiation, the ability to generate emergent topological proliferations; adaptability, the ability to manage the inputs and achieve an equilibrium; and control, the ability to influence the result according to user intentions. Thank you.